My voice is a little bit hoarse today. Apologies about that, but I'll do my best. So my name is Kaspar, and I studied renewable energy and mechanical engineering in Scotland. And so I was able to learn a lot about solar power, wind power. I went to live in Germany, and I learned a bit there as well, did the Erasmus program. Sadly, it's finished now, but I was able to learn a lot there as well. And I came back to London, and I worked on the roof doing actually installation work. I wanted a bit of a change from university to learning more about the tools. And so I learned all about plumbing and gas boilers, and then I went on to do more stuff. Now I'm doing heat pumps and solar panels. So today I'm going to try and keep you really engaged, and I've got loads of photos to show you. And I want you to just try to sort of see more about what the different systems look like, a bit of the details here and there, interests, you know, what is there about solar panels, what's there about heat pumps to know, what's interesting, what's important to know about them. So we're going to start off a few pictures of the solar panels. So what you can see here is quite a typical installation. It's called above roof. So the panels are basically a little gap off the covering, off the slates, and they've got some rails underneath that lift them off the roof. And so it's a very versatile way to fix the panels, because you can go quite close to the edges and you've got some flexibility there. So an interesting thing about this system, if you are going to have solar panels fitted like this, make sure that you have mesh on the sides, because believe it or not, the biggest problem with solar panels is birds, in particular pigeons, nesting under the panels. So actually, 4 to 5 years ago, there was a lot of people doing solar panel installation work, and they even did to the point of like rent a roof, where you'd let your roof be available for other people to put panels on, and the quality was really going down. And so some of these companies were putting panels up with no mesh at all. The pigeons were nesting underneath. The nest would get very wet. That could cause leaks into the house. It could block up the gutter. That could cause problems. And in some cases even, the nest would dry out. The electrical work wasn't done very well, and there were even fires happened because of the lack of the mesh. And so it was actually such a big problem that one of the main insurance companies that was insuring solar panel work, they went bust. And they stopped insuring solar panels because they just couldn't afford the number of claims that were coming back. So finally now, mesh is a standard part which comes along with solar panels. So the companies who sell them also sell mesh. It used to be hard to get hold of. Now it's easy to get hold of. But I just thought I'd tell you a little about that story. Some people don't like the look of the mesh, and hence that takes us to some other alternatives. Is this the right thing to, yeah? No?
On the top of the right of it, that thing that's
Sorry. No. You go for it.
I would just tell you, it's quite expensive having done retrospectively, which is what I did this year.
Ah, yes, yeah.
800 quid.
Oh, wow, okay, yeah. So that's the thing about solar panels. Because we're working on scaffolding, working on the roof, you really want to get... Pardon?
They did it by rope.
By rope, okay. Well, that's quite a lot of safety. Yeah. Okay, thank you. So we've got some more photos here. What? Testing it's working now, that's good.
just the right one.
Yeah, good. So another system then is this flat roof system. So you're very familiar with people having garden extensions, extension in the kitchen or a garden house sometimes. So we use this system. So just a quick question to the floor. Does anyone have any idea why we put this low tilt to the solar panels? Any suggestions there? Anyone? Okay, at the back, yeah?
To catch the best sun.
To catch the best sun. Good, okay. So the best angle in the UK for sun is 35 degrees. So quite steep. Water runoff, fantastic. So water runoff. So when it rains on a pitched panel, it cleans it, actually cleans off lots of the dirt. If the panels are completely flat, dirt will build up and you'd have to do a lot of cleaning. So that's why we keep this minimum 10-degree angle. If the best angle is 35, why do we put it quite low down? Why do we put it only 10 degrees? Does anybody have any ideas why that might be? Why do we go a lower angle?
The
wind damage, exactly. So the wind on these flat roofs can be very strong in the gusts and the gales, and the danger is that the panels will be blown off the roof. So that takes us to the next little picture here. You can see in this case we have ballast blocks underneath the solar panels, and the blocks actually hold the panels down to stop them getting blown away. The problem is, if you've got quite an old roof, the blocks might add a lot of weight to the structure of the roof, and it might not be strong enough to actually have that much weight on it. So this can be a good system for low down roofs that aren't too high up, maybe just 3 meters up. But the other system here, oh, it's gone off again. What? Am I doing it wrong? Go left.
Do you want to take back to the beginning, please?
Yeah, can you take me back to the beginning? So, yeah, the thing about the angle, the low angle, is that at low angle there's less wind suction force that can actually lift the panels off. When they're steeper like this, you get more wind at the back of them, which can carry them up. So the reason why I put them quite low angle is then to reduce the actual force on the panels. And the other good thing as well, if you have them at a low angle, there's less difference between the orientation, which is basically if it's facing east, north or west. If they're at a low pitch, you get more of a constant output through the day. So a south-facing solar panel will basically have its peak at 12 o'clock of energy output, whereas an east-facing panel at a lower pitch angle will have more of a kind of curved mountain output. And it's good to spread your power across the day because then you're going to use more of it in the house. So that's another good thing about having these. So here we go. So here's another example where we're actually fixing the panels through the flat roof. And that's something that's a bit more expensive because you want to have a really good fixing system that isn't going to allow any water through. Next one. Here's another system. This is an integrated solar panel. So you can actually have the solar panels flush with the tiles. It's another option. Downside of this is that the flashing needs space on the edges. And so because of the flashing space, you might have less panels than the above roof system because you're putting this flashing piece to integrate with the actual slates or tiles that you have. So that's the downside. The plus side is it does look really good. For hotter countries, this can be slightly less efficient because the ventilation gap actually helps to cool the panels down. But when they're on the roof like this, they do get hotter. In the UK, it doesn't get that hot that often, so it's still quite a good option. It's very popular. Generally, when people are redoing the whole roof, if you're doing a whole new roof, you might want to go for the integrated option. If you're keeping the roof the same, then it's quite a big cost difference to take all the tiles off to try and fit this kind of system. So that tends to be where people use it. And you can see on the right-hand side here, these are the trays, plastic trays that go underneath that create a weather-tight layer underneath the solar panels. This is a little picture of the equipment inside. So you do need some equipment as well. You need to find a space under the staircase or in a utility cupboard. You've got an inverter here, and some other switches. So that's about this kind of height as well. So if you think about that, think about how the cables are going to get to and fro. Here we've got some batteries as well. So very popular now is fitting batteries to the system. The benefit is that when there's too much solar energy, keep it in the battery, and then later on you can use it in the night time. The price of batteries has come down quite a lot now, about £2,000 for 5 kilowatt hours. It's a lot less than it used to be in the past. But I generally tend to say to people that the technology of battery is changing a lot. So we went from lithium ion, now people are using lithium ion phosphate, a new type of chemistry which is a longer lifetime, more reliable. So, you know, there could well be more changes as well coming up. And another thing that's happened recently is that some of the companies, through this thing called the Smart Export Guarantee, will actually pay you to export electricity back to the grid. 15 pence per kilowatt hour you can get from Octopus Energy is quite a good rate. So because of that good export tariff, it does take away a little bit the steam from putting a battery in. So for people who haven't got the space inside, because this is a lot of space now we're talking about taking up, you know, and London houses can be quite small sometimes, so the export payments can be a good alternative as well for that. So air source heat pumps. So the air source heat pumps, obviously we've got here an outdoor unit, blowing the air, making it very cool. So the important thing is where to situate the heat pump, where it's going to have lots of airflow. People often want to hide it out of way, get it so it's not visible, but unfortunately we do need that space to allow it to blow enough air through. I've got quite a few different pictures here of different places where we've had them fitted. So the heat pumps can work very cold temperatures. They can actually work to minus 15 degrees. So you might think that when it's cold, you know, where's the heat to actually heat the house? But if you go back to a physics understanding of energy, even 0 degrees is 273 Kelvin. So there's lots of energy in the air. It's only that water starts to freeze at that temperature. And the heat pumps have something called a defrost program, where what it does is when it gets too cold, as the air is blowing through the back of the heat pump, it starts to freeze over and form like an ice sheet. And so what it can do is it can switch round and blow heat the other way, and a big puff of steam comes off the back of the heat pump. And lots of people, if they see it for the first time, they think the heat pump's broken. They say, Kaspar, there's all this steam coming off the heat pump, quick, come and fix it. But actually it's a normal thing. The defrost cycle, heat pumps do it in the winter when it's wet weather outside.
So there was a picture of it not next to a wall. So where's the house relative to that one on the left?
On the left, very good observation. So this one is not on a wall. There is pipework under the ground, underground pipework. So we do find in many situations that the best place can be at a distance from the house. We try to minimize that distance. The manufacturers will let you go up to 20 meters distance, and the pump will still be able to circulate the heat. There is a little bit more energy loss in heating up all that water, but practically in London, often with the mid-terrace houses, the distance between a hot water tank and the heat pump can be quite a distance. And so it can still give you relatively efficient operation because under the ground, the pipe is very well insulated. We have pre-insulated pipe and it's not as cold as well. So that is a alternative that most people do go for, underground pipe work feeding to the garden-based heat pump. There's another one on the wall again. Another one there. That's next to the house. That one has also got a pad underneath as well. So to the inside now, so these are the hot water tanks. So the big difference on retrofitting a heat pump is that without a heat pump, you might be okay with a combi boiler. Many people probably have a combi boiler because a combi boiler can produce enough hot water for one shower. For many houses, if it's just one person or two people living there, hot water-wise, it's enough. So they don't need to have a tank. The benefit with a tank is you can store a lot more hot water and you can use it for more bathrooms at once. So you can have 2 or 3 bathrooms. So that's the performance benefits of the tank. The reason why we need one for a heat pump is because the heat pump doesn't have enough power to heat up cold water to get it hot enough all in one go. At one time of flowing through the heat pump, it won't get it to the right temperature. It has to go in smaller increments. So what it does is, as the tank is, say, 20 degrees, it will first warm it to 30 degrees. As it gets up to 30, it goes up to 40, and gradually it takes it up to about 50 degrees, which is warm enough. So a typical shower would be about 45 degrees, would feel quite warm. And so the heat pump's able to go above that to have warm enough stored hot water. So you can see the space that we need is a little bit bigger than what you might have in a typical laundry cupboard. So sometimes we do have to look for spaces. There are different ways we can configure all of the equipment. This is a project we've done recently. It's actually a church building where we've come and fitted 4 heat pumps. Not in those locations, that was just when we delivered it on the roof. But that's obviously quite high power. So the thing about the heat pumps is, people ask me, will it work in different types of buildings, maybe buildings that aren't so well insulated? And it's definitely true that the better insulated the building is, the more efficient the heat pump is. And it's not just a relationship of half the heat loss, double the efficiency. When we lower the temperature of the system, when we have a less piping hot radiators, more lukewarm, we actually get a better ratio of efficiency from the heat pump. So if you have half the heat loss, you can get even 3 times lower running costs. So it really does pay back to invest in fabric improvements where it's possible, you know, where it's affordable to do it in stages to improve the building. But if we can't, in this case, we didn't improve the building. Instead, what we did is we made sure that the power that we needed, we could actually deliver to the building at a low temperature. So we changed all the radiators. I had some old column radiators that weren't too big, and we put in much larger convector radiators with lots of surface area. So if you have the design done, you have calculations done, if you have enough surface area, then the heat pump can work efficiently, even with very high amounts of heat it has to deliver.
So did they go on the roof?
They went these ones onto the roof, yeah. So the roof, this roof here is quite accessible. It's got a ladder that goes up through an access hatch to go onto it. So some manufacturers don't like having the heat pumps on the roof without really extensive balustrade around the edges and a fixed staircase in position. But Mitsubishi, in this case, they don't mind having some form of access that's relatively safe to go up. Obviously, if there was a warranty issue with these heat pumps, then we'll have to get some lifting equipment to take them up and down, which can be quite expensive in some cases. So we don't tend to put a roof as the first option. This is more of a commercial installation. Typically for residential, we'd want to put them at ground level. It's easy to access, easy to get to, easy to move backwards and forwards, because they're quite heavy. They're 150 kilograms in some cases, so you need 4 people to maneuver them around with lifting equipment. And here we've got the lifting equipment we use to take up to the roof. We've got the plant room with all the pipes. So that was quite extensive heat pump installation. And here's a few little pictures of a wooden enclosure. So it's possible to hide them if you want to with like a louvered paneling. So this is louvered paneling, so the air can still flow through, but it's not visible. So that can be good. Some people have them at the front of the house and in something that looks like a bin store, looks like a bike shed, which often you see in front of houses. So that can be a way to actually have it. The front of your house, you don't use it for much, you just come in and out. So it can be a good place to put a heat pump, which, you know, would otherwise take up space. Question there?
Is there a risk of them being stolen for the front of the house?
Absolutely, there is a risk of them being stolen. We did have one project where they hadn't yet put any enclosure around it, and somebody came and just literally cut the cables and just went off with the cables. So there are obviously certain people around who will do things, you know, without too much logic. But generally, once you've got the enclosure around it and it's not visible, that does detract enough away from people, because it's a big operation to actually try and steal it. You know, there's a lot of work. So you have to be quite a, you know, qualified heating engineer to know all the things to do. You know, you've got risk of electrocution, risk of gas explosion, risk of heating hot water pipes going over you, like, you know, so I haven't heard much about them actually being stolen. But yeah, if you have an enclosure that looks pretty robust and you can't see inside, I mean, that tends to be fairly good. These levers are at a 45-degree angle.
45
Yeah, and I've got some pictures here. This is a really nice one made of cedar wood. So that was quite an expensive construction there with some steel framing at the back, a little bit over the top. But we've also got other examples which are a lot cheaper and simpler, which also can hide the heat pump.
So just on the case of that,
Yep.
is it enclosed at the top as well? Or is it
So it doesn't need to be at the top necessarily. Some do enclose on the top, but the equipment is designed to be in the rain outside. So that is, you know, perfectly okay, yeah?
So earlier you said about wind. Is it just that
Yep.
it needs to be getting air, but not necessarily wind? It doesn't need to be strong.
That's right, not wind, just airflow. So we do have problems, for example, some people often want to put them in like a light well at the front of the house where stairs go down. And the issue is, when you blow cold air into a depressed area, the cold air stays where it is. It doesn't rise up. And so you can get quite low efficiencies in that situation. If you have a courtyard, for example, that's all enclosed, and you have the heat pump blowing cold air, again, it won't really change. So you want to have the heat pump somewhere that's got relatively free area around. That's why gardens are good, because you often get flow-through of air in the garden, or front garden can be good as well, where you've got the street, obviously, it's quite a big area. So. Say that again. Well, it's a very good question, because the problem is the manufacturers don't manufacture or don't guarantee efficiency, because their unit is rated at different efficiencies and different parameters. So it can work, and you can't go back to them and say, my bills are too high. They'll say, well, is it working as it's supposed to? So that's where we have to do this kind of on-site appraisal as to the efficiency. But I have had some situations. I went to one place in Battersea where they actually had it inside a building, and they had a louvered window, and the heat pump was inside the building blowing air out. And they said to me, I don't know why, every year we have to get an engineer to repair everything. It breaks down every year. And I said, I don't think being inside a garage is the best place for it to be located, because it was blowing air against this louvered shutter, and most of the air was just coming back into the room. It was freezing cold in there in the middle of the summer. So that was the first time it really was obvious to me, that the location is quite important. So, yeah.
Kaspar, can we ask you, if you're taking questions
Yep.
from the floor
Yep.
during the talk, would you repeat the question so that it
Yeah, no problem.
goes on
Sure,
to the
sure.
transmission?
Sure, I'm pretty much... Well, I'll do a few more minutes, and then we'll do lots of questions, if that's okay. Yeah? So the last thing I was just going to talk about is ventilation with heat recovery, which is another thing that my company do as well. And this is really something to do when you're doing a bigger building project, when you're doing maybe a whole renovation. Because what we're looking here is we're looking at getting air from outside to bring it into all the rooms, and then extracting warm air from the bathrooms. And before that warm air goes outside, it comes together in this heat exchanger, and we recover the heat that would otherwise just be blown outside. And that goes back to warming up the air that comes in. So for example, if it's 0 degrees outside and 20 degrees inside, your 20-degree air will go outside, and it will warm up the 0 degree to about 18 degrees. So you get 18-degree fresh air coming into the house. So it's a very efficient way to keep the house well ventilated. So what you can do in this situation is you can have all of the windows closed. You don't need any trickle vents, which otherwise you do need trickle vents. You can shut them, and you have very good indoor air quality. Now, it's, as I say, it's a tricky thing to retrofit, because the ducting has to get everywhere. You have to have ducts that go to all the different rooms. So it can be difficult to do. But if you are doing building work, more and more people are doing this, because we've got systems, and I've got a few photos to show you of the units. So you can see they're quite big. They're like washing machine size. And you can see all of the air coming in, this one here through the roof, that one there through the wall, and then down into this ductwork system that goes to all the rooms in the house. The benefit is, if you've got rooms that haven't got very good ventilation, like in basements, for example, this can really improve the air quality, sleep quality, concentration, and also health as well. People who suffer from asthma, things like that. It's filtered air as well. It's got a filter. A lot of the fumes that come into the house are actually filtered. So it's a really interesting technology. Obviously, it is quite expensive to do, and ranges between £6,000 and £12,000 for a whole house, basically. But when you've got that space open, not including all the boxing work and things like that, building work you might need to do. So you can see, now this particular system here is called a semi-rigid system, or radial system. So you've got a centralized box, and then from that box, one pipe goes to every room. And the benefit there is, if people are talking in different rooms, the sound doesn't travel across. Because when you have a branch system that branches off, noise can travel between the rooms, and then you lose privacy. So you have to put in these big boxes to attenuate the noise from going between rooms. But in this system here, because it's an individual pipe each, by the time the sound gets back through the pipes, it's already reduced in sound. Also, the ducting is very easy to clean. You can clean it because it's one continuous piece of duct. There's no joints. Some of the other ventilation systems have got screws that go in and tape, and it can easily miss out bits, and you can have air leakage. So this is a much more high quality system, and it's become quite affordable as well to put in. It's similar to electrical conduit. You can see here quite a historic building, Hampstead, where we're putting the system in. The system suffers a lot from damp, humidity issues. They're doing lots of works to improve it, but this MVHR system as well will also help as well to improve the air quality. So, and you can see there how it kind of fits in to the voids, ceiling voids, things like that. So I know this isn't about heat pumps, but I thought it was just interesting to show everybody. And there you got the outlet, so that's the air outlet where the air comes into the room in the ceiling. and some of the roof vents as well. So just to give you an idea of what's involved in those kind of systems as well. But I think that's pretty much the end of all the photos. But yeah, if you want to pass the microphone around, we could do some questions. Go back to the heat pump photos.
Can you just explain how the three of those things work together and whether it's possible, well, I know it's possible to have one or not the other, but the best way of combining the three?
So the question was, these three technologies I just talked about, solar panels, air source heat pumps, MVHR, to combine them. So yeah, what happens a lot is people tend to not quite understand the differences and kind of put them all together as one thing. But these are completely separate, independent technologies that are just completely different things. So the solar panels, we're producing power to reduce your energy bills, to contribute to reducing how much you're paying for your bills and your CO2 emissions. You've got the heat pump, which is basically just direct replacement for the gas boiler. The gas boiler used to give you underfloor heating or radiators and hot water, and that's now been replaced by the air-to-water heat pump. And then you've got the MVHR system, which is basically a very efficient fresh air system. And it's mainly all about the winter. In the summer, when you've got overheating, you can open the windows. That's not a problem. You can to get rid of when there's too much sunshine. The main benefit of the MVHR is all about the winter. When we're in the house a lot, it's very dark outside, working from home, and you want to have good air quality. So they are separate systems. There are ways in which you want them to be maybe kind of aware, in coordination with each other. So for example, there's lots of cold air around the heat pump. You don't necessarily want that to go into your MVHR system, things like that. But generally, the best way to understand them is just to really separate them out to see the differences.
A sort of linked question to that.
Yeah.
So if you've got your solar PV and you've
Yeah.
got a heat pump,
Yeah.
do you find that in like the spring and the autumn when you're still getting a reasonable amount of sun but it's quite cold, is that contributing the electricity to the heat pump to reduce the running costs?
Absolutely, yeah. So it's a really good point you made there, which is that the payback from a solar installation financially is proportional to how much energy you use. So if you use very little, you end up exporting a lot, sending a lot back. And typically with a gas boiler, people might only use 30% of their solar energy. But once you add in an air source heat pump that's using a lot of electricity, that then can really go up to 50, 60% of your solar energy you can use in the building. Particularly if you do things like timing it to work in the daytime, doing hot water in the daytime to coincide with solar energy as well.
So I have a fundamental question on the technology. I mean, obviously
Yeah.
this is taking cold air and
Yeah.
then it's electrically heated up. Is that essentially the energy source which heats up?
So it's a good question, yeah. So something that electrically heats it up is an electric heater, not a heat pump.
Okay.
So what the heat pump's doing is it makes the cold air even colder and uses that negative energy it's made colder and then makes somewhere else even hotter. It's transferring heat from one place to another place, like a fridge, just like a fridge. And the method it does it is the refrigerant cycle, and it's using the gas, basically, change of state. So when something goes from a liquid to a gas, it's a higher energy state, it's got more energy. Just the same gas, same amount of volume of material, it's got more energy. And then when you bring it back down to a liquid again, then it's a lower state of energy, so it gives off heat. So you can force energy to be transferred by making it change what state it is, making it go into a gas and then go back into a liquid again. And that's basically how they move the energy from the air then into the wet heating system.
Good, thank you. Can I just ask one more question?
Yeah.
A lot of this is very sort of aimed at single residences, yeah?
Yeah.
Obviously, London is full of flats and in leasehold properties or for shared freeholds at best. How does this work if you have multiple units?
Yeah.
Do you need multiple heat pumps? Each of them have a heat pump, or is there a
Yeah.
way to proportion then the overall energy?
So the question, I think everyone heard. Okay. So basically, it's a really good question. It's about the limits of these technologies, where you can apply them. So London is a very densely populated area, very dense in our services, service distribution. How can we get as many people as possible into a small area as possible? And so that does squeeze these technologies into their limits. And there are limitations. For example, you need somewhere for the air source heat pump. So if you have a tower block or a story building and people don't own any outside space, then how are they going to have an air source heat pump? And so when it comes to services for your building, it does also come back to legal issues and ownership. Because if you share a technology between people, a third party will have to maintain it and manage it to be responsible when it breaks down. You can't really sell a house that shares something between other people that doesn't have a third party entity who's going to actually organise that. So generally always, each service is for that one owned property. So when you have a building with lots of houses, the ground floor properties that have gardens, they can have heat pumps. The top floor properties that have roof spaces, they can potentially have heat pumps. Some rooms that maybe have big balconies, maybe they can have heat pumps. But houses that don't have any of those are quite limited what they can do with that, because they have to look at other options, other things that are more of a compromise solution.
Hi. When you're retrofitting MVHR to, say, a Victorian property,
Yeah.
can you install an efficient system even with the compromises that have to be made dealing with, an existing property? In other words, for example, if you choose not to put in false ceilings in order to accommodate ducting or efficiently sized ducting because you don't want to lose the cornices or whatever it might be, can you still, within the fabric of an old building, do a
There are
good
lots
job
of
with
ways to do it.
MVHR?
Yeah. So with MVHR, there's a few different issues. So one issue is space. So that you can put things in the ceiling. You can have you can put things in the wall. You can put things in a skirting board. You can make a wider skirting. You can run around eave spaces of a loft and go down into the ceilings below. You can go under the floor. There's quite a few different options how you can make things work, but generally you need access. Generally you need building work to enable that. The other side also is people ask, what about if it's a leaky building? There's lots of holes everywhere, air's coming in and out. So what you'll find is even with relatively leaky buildings, the main air leakage is open windows and open trickle vents. And if you're able to shut those windows and shut the trickle vents, that alone is almost 15-20% saving on your heat loss, in some cases even more. So that can actually be quite a big enabler with MVHR as well.
How noisy are these units, and what's their lifetime before the bearings start to wear out and they rattle?
Very good question. How noisy? So this particular unit here is 11 kilowatts. It's for quite a big detached house, four-bedroom house. It's 60 decibels, a metre away from it. But the nearest neighbour's window or place is going to be disturbed. It's only about 42 decibels, which is quite quiet. It's something like a fridge sound in your kitchen or the sound of traffic that's not very close, quite far away. So it's hard to say specifically. Smaller units can be really quiet. I've got one in my house which is a 5 kilowatt unit, which is for like a smaller building. I've got more insulation, so that works for me. And most of the time you don't even know it's on. You just feel the air blowing, but you can't actually hear any noise because the background noise is much higher. So there is some range in that noise level, but generally the units have been made now really to be quiet. And on lifetime, you're thinking about 15 years generally. They should be fine. We give 7-year warranties with any heat pump that we install. And so, you're looking at quite a decent lifetime of them.
Solar panels.
Yeah.
So I was one of those poor schmucks that put solar panels on about 4 years ago.
Right.
I was naively...
Keep the mic close, please.
I was naively assuming it was going to last 10 years or something like that. Is that a fair assumption for solar panels of that generation? And is there a business case for replacing them with higher density, better ones in the near future?
Solar panels. There are solar panels right now in space powering satellites, which have been there for 50 years and longer. 50-year-old solar panels still working now, powering the satellites. So the technology of solar panels is incredibly reliable. We know exactly how they work. They have a degradation level of about 0.5% per year of power output. So after 25 years, they're about 85% power output. So they work pretty well for a long time. The bit that needs replacing is the inside equipment that we looked at before, the inverter. Because the inverter has to disconnect when there's no more power anymore. It can't just stay connected all the time. So when the sunshine goes down and when it's nighttime, it mechanically disconnects itself, mechanically reconnects. So because of all this mechanical movement, eventually things start to wear out. Plus you've got an inverter which is creating this AC waveform, and that has heat, power, electronics. Any electrical component, the method of failure is always through heat build-up, and that makes the copper elements in the metal more brittle, and that makes the connections snap. So there is, in the inverter and the power electronics, that's where you get the issues. And generally they have at least a 5-year warranty, sometimes 10 or 12-year warranty that you get with the inverters. But the cost of replacing them is much smaller than the whole solar system. So it can still give you good paybacks by having to replace the inverter 15 years down the line.
I have a couple of heat pump questions. People seem to have underfloor heating downstairs and radiators upstairs. Is there any reason why you couldn't have underfloor heating downstairs and upstairs?
Great question, yeah. So underfloor heating, downstairs, people often have a concrete screed. So they have a cement-based flooring, basically. And when you do that, it's very cheap to put pipes within the cement. In terms of cost-wise, doing that versus doing radiators is pretty much the same thing. Upstairs, if you're going to put pipes in the floor, you have to put an actual board layer, which is going to accommodate the pipes. Now, that can either be metal trays within the joist, or it can be an overlay board. But either way around, it tends to be quite a lot more expensive than just putting radiators, because you've got the plumbing work to pay for, and you've then got the carpentry work to make this layer for the pipes to go in. So that's why most people tend to, from a cost perspective, decide to do what you mentioned, underfloor and radiators. But you do still get people doing underfloor everywhere where they want to, and they don't mind the additional cost.
And my other question was the hot water cylinders.
Yeah.
Do you get a warm area around them, like the old-fashioned airing cupboard? Do you get some warmth?
Yeah. So there's a big difference to previously. So. When they were first came out, hot water tanks, they weren't even insulated. They were just literally a copper. And the standing heat loss, the heat that came off, was quite significant, hence the airing cupboard idea. But as time has gone on, the building regulations have tried to get us to understand that it's not just about heat anywhere in the house. You want heat where you need it. So the house has a heat demand. It needs heat in some rooms, it needs heat in other rooms, and it doesn't need heat in other places. So you making places unnecessarily hot is a waste of energy and increases your running costs and a waste of efficiency. So now the building regulations specify that all the pipes should be insulated in the house, all of the components should be well insulated, so that we direct the heat that we need to go to those rooms that are too cold, that need to be heated. Because all the time heating engineers say, I'm not going to insulate those pipes, it's inside the building. Why would I insulate it? But if you think about it, we don't need heat constantly all the time in the house. We're not continually have the heating running. We switch it on, we switch it off, we switch it on, switch it off. But when we don't insulate those pipes, they're always draining, they're lagging away heat to places that we don't need to be hot. So that is the reason why things have changed a lot. So now plant rooms, if they're done well, aren't as hot anymore, but there will always be some heat that comes off components and things like that. I've got some nice pictures of plant rooms, didn't I?
So I was just going to ask, with the plant rooms, how do you get around the issue of the Legionnaires with the water storage? Is that still an issue, or has that changed?
Yeah, perfect. So that was never an issue because they knew about it. And so Legionnaires basically is that when you've got hot water in the tank that is between 20 and 50 degrees, for a period of time, bacteria can start to grow within that tank when it's between 20 and 50 degrees. So like lukewarm water, when it's just in there in the tank. So because the heat pumps are only heating up to about 50 degrees, which is enough for us, there is this risk that if the tank has been between that range. So what most heat pumps have is a method with your backup immersion heater. So the backup immersion heater is an electric heater that you can use when there's a problem with the heat pump. You can switch on the backup heater. So they have a program that uses that and switches it on for a couple of hours a week just to bring it up to 60 degrees and sterilize the tank. And now the latest range of heat pumps have got a different refrigerant inside. We've gone back to a much older refrigerant called propane, which is less harmful for the environment. And that can actually run up to 75 degrees, so it can easily, the heat pump itself can sterilize the tank. So that's the different ways you can do that, yeah.
I've got another question. I mean, I can envisage this kind of heat pump, as you showed, being on a roof. Now the question is, often we've had these cold water tanks in the roof space, yeah? I've removed mine immediately, but that could be the space for a hot water tank. But now the question is, do they all come in this cylinder, or are there other shapes?
Very interesting question. I love that. Okay, so the issue is the loft spaces are often not very high, and the old water tanks are often long, like you say. If you have a horizontal hot water tank, the problem is that we don't get stratification in the tank. Stratification in vertical tanks is where the hot water is physically lighter than the cold water, rises to the top, and the cold water is denser and goes to the bottom, like you have in the ocean currents. And that creates a boundary between the two different waters. You can heat up water to a temperature and it won't cool down. It will stay hot for hours later while there's freezing cold water below it. And that means that you keep your hot water usable temperature for a long time. With a horizontal tank, because there's so little height difference, you don't get stratification. And as soon as you draw off some water, cold water goes in and it just mixes everything up. And so after just half an hour, your 50-degree water is now 35 degrees. It's still warm, it's just not warm enough. And so you have to keep switching on the boiler again, top it up again, and it's a very inefficient operation. So we don't use, well, I don't like to use horizontal tanks with heat pumps. Instead, I like to always use a vertical. There are vertical sides that are more wider and shorter that can work in certain loft spaces. And we do often fit tanks in loft spaces as well. We do often do that where there is enough ceiling height, standing height, that you can get a tank up there as well. So.
Hi, yeah, another one from me. I wondered if you could say something about the incentives that are there now to install a heat pump, and also how you would choose an installer, because there's going to be lots of different people out there who claim to be able to install them. What should you be looking for?
Yeah, good questions, okay. So the first thing is the government have a grant called the Boiler Upgrade Scheme, £7,500, pretty much everybody is eligible. So pretty much anyone who wants to do a heat pump, even in a commercial property as well, pretty much any shop is eligible to put a heat pump in. The minimum requirements are you have to get an EPC, which is very easy to do, and it can't be a new build. If it's a new build, they kind of have to put in heat pumps by regulation anyway, so they don't get funding unless the new build is owned by a person, and then they can claim the grants. But if a developer's building a house, they don't get the grants. But pretty much anyone else can get the grant. There's £7,500. The second question, how to find a good installer. There's a accreditation process called the Micro Certification Scheme, MCS. And MCS has been around for a long time now. It's for solar, it's also for heat pumps. And it's basically where the installers are checked by this other third party. And every year you have to pay membership with them. And if I do anything wrong to any customer, that customer can go back to MCS, they can go back and they can basically stop me from doing any work. So they've got immense power over people who are registered with them. And it's a really good way to, there are other things as well, like there's a renewable energy consumer code, is a code that I've signed up to, which says I have to do various things to give homeowners fair treatment. So I can't use pushy sales tactics like saying, if you go ahead, I'll give you a discount in the week, things like that. You're not, actually not allowed to do things like that. There's a database online, it's called the MCS Installer Search. You put in your postcode and it literally shows you businesses that are registered in your area. And so you can easily find different companies that are registered and you can get quotes from them. Yeah.
Can I ask about solar panels?
Yeah.
We contacted Octopus and they gave us a quote for doing solar panels, all very good. And then they said no, they couldn't do it because, and what they said was that our main bedroom is in the attic, and they said that they wouldn't install on a roof, which was is that?
Yeah. So
and
Octopus,
my second question
Octopus Energy, I love them. They're really innovative. They're pushing the boundaries, but they're also driving me crazy because what they're doing is they're subsidising their own solar and heat pump business with all the money they make from selling us oil and gas. So they're intentionally making it much cheaper than a normal business could ever afford to. And then what they're doing is just giving everybody quotes, but not actually checking, not doing a site visit if they can actually do the work. And so I get all these people come to me and say, why am I more expensive than their Octopus quotes? And I say, well, that's fine, just go to the Octopus person then. Oh, they won't do the job. So I'm just like, the net effect is basically just making me look like I can't run my business, you know. So that's the difficulty. But the intention behind the Octopus is to get more trained installers, to reduce the cost for everybody. So they're trying to push in the right direction, but the way they're doing it obviously is a little bit unorganised, yeah. But
there's no reason, really.
The reason is that with this work, like what I showed you in the beginning, the different mounting schemes, some things are easy and some things are really hard. For example, taking out slates is a lot of tough work. You have to put a slate ripper under the slates, you have to knock out the nails, break the nails apart, and then the slates come out. You've got to be careful not to break any slates while you're doing that. So it's really, really difficult, skilled work. Working on a concrete tile roof is completely easy. Just pull off the concrete tiles. They're not even fixed down. And you can get to the roof below to fit the system. So some solar installers just like easy jobs. What goes along with it as well is all the design insurance, all the calculations, the wind loading, things like that. You know, if people aren't sure and they aren't able to get that guarantee that they think it's going to work, they just say no to it. So that's the reason why you get that kind of thing. Also with the heat pumps as well, you know, if the installation looks a bit difficult, if you've got an old system, we had one very hard house where we couldn't find the incoming mains tap to switch off the water to the house. There was just no tap in the house. There was one tap, you close that tap, and there's still water over there. And there's a tap over there, close that one, there's still water upstairs. So, and the problem was we couldn't give them a balanced water flow from the tank. So it was very difficult. So that's another reason, again, why people sometimes, you know, say no to work, what they should do.
I think I can see that there are more questions, so there's a lot of interest, but we're running a little bit over the time that we said. Maybe it would make sense at this point, if you don't mind staying around for a bit, if we draw a close to this part. Everybody can get another cup of tea, whatever, if they want, and then Kaspar has said he'd be willing to stay around and answer some questions more informally. So I'd like to extend a very big vote of thanks to you, Kaspar. Thank you very much for coming. So what we'll do now is there's an opportunity for another cup of tea or coffee or anything that you want to get, and there'll be an opportunity to ask Kaspar some questions informally. Thank you.